Evening, I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest video, and in this video, I'm going to take a look at the Southeast Ridge and U.S. winters. On the title slide here, I'm showing you an example of generally what a Southeast Ridge would look like. We're looking at the 500 millibar heights and anomaly map here. 500 millibars equating to about 18,000 feet above the ground. And what you see here is these deep oranges, these deep orange colors, generally extending along the U.S. East Coast out over the North Atlantic Ocean. This is an association where we had a southeast ridge in place. And this happened back in February of 2022. I will get more into details about, the synoptic pattern, where you would expect to see the troughs, vice the ridges here in the following slides. But just kind of wanted to show you as a little appetizer here of what a southeast ridge would look like. Anywhere in these deeper orange colors, by the way, we have anomalously above normal heights. Anywhere where you see the green coloring, for example, in the Four Corners region here in the western U.S., that green would indicate below normal heights. So let's get right into the video, starting with the overview. Due to its strong influence in producing unseasonably mild temperatures across the eastern U.S. during the winter season, I decided to look back at the past winter months when the Southeast Ridge was the dominant synoptic feature. And I'm going back to 1979. In this particular look back, I'm not looking at the entire winter, all of the three meteorological winter months of December, January, and February. I just went back to look at past winter months to see when the Southeast Ridge was actually the dominant synoptic feature. So this is really my motivation in doing this research video. Knowing that anomalous weather can occur in the wintertime and, seeing these unseasonably mild temps across the east really had me thinking. The Southeast Ridge, by the way, has been more dominant in previous winters than others. Additionally, towards the end of this presentation, I will examine a potential connection between above normal hurricane seasons across the North Atlantic, where we would see lower pressure more frequently, and the establishment of higher pressure, or perhaps the development of a Southeast Ridge across that same area of the western North Atlantic the following winter. Now, just to give you an overview of things, we typically see two main synoptic weather features that influence the weather conditions during the winter across the mid-Atlantic and southeastern U.S. We see upper troughs as well as upper ridges. Now, we can see a fast progressive pattern with quickly moving upper troughs and upper ridges kind of moving fast from west to east. Or during the winter, we will see what's known as a blocking pattern, where a upper trough or upper ridge stays in place for long periods of time. Now, when these areas, the southeastern U.S. as well as the mid-Atlantic, are influenced by upper troughs, we typically see cold and stormy weather. On the other hand, when we have an upper level ridge in place across the mid-Atlantic and southeastern U.S. during the winter, we typically see mild and dry weather. So when an upper trough digs into the western U.S. as well, upper level heights typically rise downstream across the eastern U.S., supporting the development of an upper ridge. And the deeper that trough digs into the western U.S., the stronger that upper level ridge will be downstream across the eastern U.S. So when the Southeast Ridge establishes itself, overall what we'd expect to see is cold Arctic air unable to reach the southeast and mid-Atlantic coastlines. And that cold Arctic air is going to remain positioned well back to the northwest. And it's typically going to be associated with a trough. When we see the Southeast Ridge in place, we can also see these record high temps in many locations, many eastern cities in the winter season. And with the Southeast Ridge, the weather may also be unseasonably warm and dry for extended periods of time. So that kind of gets into the blocking type pattern that I was mentioning. A massive upper ridge, what it does is acts as a roadblock to other systems. Storms must go up and over that ridge. So basically the way things work is areas of lower pressure, they seek out areas, the paths of least resistance, and those areas of low pressure want to seek out lower troughs or lower heights in the atmosphere. So generally your storm systems, areas of low pressure, are going to be unable to move through an upper level ridge. Instead, they have to go up and over that ridge. And that's what results in the drier weather. There's usually at least one time period when the southeastern ridge is going to influence the weather during the winter season. All right, so just to start things off, I wanted to talk about the weather differences between upper troughs and upper ridges. Over here on the left, I'm showing a graphic of an upper level trough. These red arrows indicate the wind direction through the trough axis. This dashed vertical line, black dashed line here, represents the trough axis itself. And what's so significant about the trough axis is it's the point of lowest pressure or lowest heights. They generally occur right along this trough axis, this line here. What you'll see when you're looking at the 500 millibar chart is you'll see geopotential heights. And whenever you see the geopotential heights take on more of a U shape like this, what we're showing here, the U-shaped pattern, that's associated with a trough. Typically with troughs in the upper levels, you'll see cold and unsettled weather conditions. On the right, on the other hand, we have what's known as upper level ridge. These red solid lines are lines of equal heights, or lines that are known as geopotential heights. In general, this is the ridge axis, the pink vertical line, and along the ridge axis, we typically see the highest heights. Okay? And what is so significant about upper level ridges is they're associated with warm and dry weather conditions. And you'll notice it's the opposite shape of the trough. The trough shape is a U, and the ridge is an upside down U. All right, so wanted to show you what a classic Southeast Ridge setup looks like in winter. Over here on the left, I'm showing the European model. These are the 500 millibar or 500 hectopascal geopotential heights in decameters, as well as the anomalies in meters. Anywhere where you see the orange coloring, we have above normal heights. Anywhere where you see the green coloring, the blue coloring, that's below normal heights. So this actually occurred back in 16 February 2023. This is your 500 millibar chart here on the left with these height anomalies. This blue H represents the high height center itself, which was positioned at this time just to the east of Florida. And this green sawtooth line indicates your ridge axis, the height, the line at which you have the highest heights along it. And so what we had in this case with the 500 millibar pattern is we had a closed low situated over southern Colorado. The green colorings indicating very, very anomalously low heights. And we had a trough that was digging into this Four Corners area here of the western U.S. As the trough digs and digs deeply, the deeper it digs, the higher these heights are going to build downstream across the eastern U.S. So this was a case where we had a southeast ridge established. Over here on the right, I'm showing you the temperature anomalies now. For the same time period, 16 February 2023, look at how cold the temperatures are, below normal they are, the purple coloring, across Colorado, Wyoming, parts of Utah into Arizona, New Mexico, associated right near the closed upper level low, as well as the base of that trough in the west, much below normal temperatures. Meanwhile, to the east, associated with that southeast ridge, we have anomalous warmth occurring from Texas all the way through Tennessee. Basically, the heart of the warmest temperatures, or the highest temperature anomalies, were Ohio, Pennsylvania, New York State, where these anomalies reached up to 33 degrees Fahrenheit above normal for parts of western PA as well as western New York states. So this was an anomalous warm period, and it's really of no surprise when you look at this map, this chart here on the left, showing that southeast ridge firmly in place. Now, I did want to mention that this circle area here in the right-hand graphic, this is my area of interest for this presentation. This is the area where we're looking at, whether there's a southeast ridge or not. All right, so let's look back at past winter months. Now, I went back to 1979, but I went and looked at the various reanalyses to determine when the southeast ridge really took effect on the weather across the east. And so over here on the left of each of the upcoming slides, I show you the 500 millibar heights and anomalies. So whenever you see orange and yellows, we have above normal heights, and that's typically associated with the southeast ridge. Whenever you see the blue coloring, that's indicative of upper level troughs, it's associated with cooler and unsettled weather. All right, so December 82 here on the left, 500 millibar heights and anomalies. You clearly see the orange and yellow coloring from the mid-Atlantic into the western and North Atlantic Ocean. And these are the temperature anomalies in December 82 on the right, showing well above normal readings in the orange colors and the deeper orange colors here, specifically across Illinois, Indiana, lower Michigan, Ohio, as well as Kentucky, where temperatures were 6 to 9 degrees Fahrenheit above normal. You also had above normal readings all the way up and down the entire East Coast. And just to kind of throw some fun facts here, Christmas Day 1982 was a very anomalous day associated with the Southeast Ridge as it extended northwestward towards the Midwest. Places like Cleveland, Ohio were 66 degrees on Christmas Day 1982. Chicago and Detroit, 64 degrees Fahrenheit. Buffalo, New York, 64 degrees Fahrenheit on Christmas Day in 1982. So it was a very anomalously warm holiday season back in December 82. Moving ahead now to February 1990. Go ahead and look at the chart here, the 500 millibar height anomaly chart on the left, showing the orange coloring. That is the highest height anomalies, okay? And those were positioned over the mid-Atlantic into the western North Atlantic. And no wonder, it's not a surprise what we're seeing here in the temperature anomalies on the right. Beneath that upper level ridge, we're seeing anomalous warmth from the Tennessee Valley eastward to the mid-Atlantic coast, Virginia, the Carolinas, Georgia, even into Florida, much above normal. We're talking 6 to 8 degrees Fahrenheit above normal in the mid-Atlantic back in February of 1990, directly beneath this anomalously high height anomaly area, this upper level ridge. Moving ahead now, a little bit later that year, December 1990, showing the 500 millibar heights and anomalies on the left for December 1990. The yellow coloring here, we have ridging over the mid-Atlantic and the southeastern U.S., extending northward towards Pennsylvania and New York State, even extending back towards Indiana and Ohio. And what would you know over here on the right? Look what we have beneath that ridging. We have above normal temps again from Florida, Mississippi, Alabama, Georgia, Tennessee, the Carolinas, Virginia, northward to New England. The highest or greatest anomalies were generally across Virginia and North Carolina, as well as parts of New York State. It was much colder generally to the west of the Mississippi River, associated with troughing, specifically over the northwestern U.S. and Idaho, Montana, Wyoming, as well as Nevada and eastern Oregon, much below normal, the purple coloring, associated with troughing. December 2006, 500 millibar height anomalies on the left, the yellow coloring indicating where that upper level ridge was in place, higher than normal heights from the western North Atlantic through the Virginia area, extending up to New England, all the way up into southeastern Canada, even all the way up to southern portions of Hudson Bay. And the Midwest is also included in this. You in the upper Midwest, Minnesota included in this ridging. And look at the temperature anomalies for December 2006 on the right. We had one area of much above normal weather across eastern Dakotas into much of Minnesota and Iowa. We're talking 5 to 9 degrees Fahrenheit above normal temperature anomalies. And then we had another area which was well above normal, Pennsylvania northward to New York State, Vermont, New Hampshire, Massachusetts, portions of Connecticut, where the temperatures were on the order of 6 to 8 degrees Fahrenheit above normal. It was also above normal for the mid-Atlantic, Virginia, 4 to 5 degrees Fahrenheit above normal in December 2006, all the way down towards Florida, where we were 3 to 4 degrees Fahrenheit above normal. December 2015, this is like one of my favorite months to look back at because it was so anomalously warm in the east. The graphic here on the left really shows that orange coloring, extremely above normal height anomalies across the mid-Atlantic, extending across New England, all the way back towards southeastern and even working its way northwestward towards central Canada. Just anomalous ridging going on. And look beneath the ridging here. Anywhere east of the Mississippi River really took a major hit as far as warm anomalies. The brown coloring over a large swath, a large area of the eastern U.S. We're talking 9 to as much as 13 degrees Fahrenheit above normal in this brown shading. By the way, this was the warmest December on record for the lower 48, December of 2015. It beat a previous record set all the way back in 1939. And the mean temperature, by the way, the mean temperature for the lower 48 was 6 degrees Fahrenheit above normal in December of 2015. January 2017, we see the ridge a little bit more suppressed here on the left-hand graphic for the 500 millbar heights and anomalies. Look at the yellow coloring here. That's the focus area from northern Mexico through Texas, Louisiana, parts of Oklahoma, Arkansas, Tennessee, and Kentucky, and Virginia, southward to Florida. We had an upper level ridge in place, and then the temperature anomalies for January 2017 on the right, showing well above normal readings over that same area where the ridge was in place. Eastern Texas, Louisiana, southern Arkansas, Mississippi, Alabama, Georgia, Tennessee, and Kentucky. Even stretched northward a little bit towards the Ohio area, as well as all the way up to Maine. I mean, Maine, you were 6 to 7 degrees Fahrenheit above normal in January 2017. The coldest temperature readings were over the northwestern U.S., in association with this blue coloring on the left-hand side here. That's associated with an upper-level trough. February 2018, let's go there. What we had here on the left, 500 millibar heights and anomalies for February 2018. The yellow coloring, we have ridging across the southern U.S., up the East Coast. And then the temperature anomaly distribution here on the right, just unbelievably warm February in 2018 for New Orleans, Biloxi, Mobile, Pensacola, Panama City. Tallahassee was 9 degrees Fahrenheit above normal. Northern Florida, Gainesville, 9 degrees Fahrenheit above normal. Up north to Atlanta, 9 degrees above normal. All the way up into the coastal Carolinas. I mean, we're talking Maine to Virginia, you're running 6 to 8 degrees Fahrenheit above normal in February of 2018. The coldest temperatures were 14 to 19 degrees Fahrenheit below normal across central and eastern Montana in February 2018. Now, I want to make a point out about this, a main point about this slide. This is your, on the right-hand side, this is your typical temperature anomaly distribution with southeast ridges that influence these areas, the southeast and mid-Atlantic. Generally, the whole East Coast could sometimes be influenced like this during the winter. The trough and the coldest temperatures are going to remain well to the northwest across the northern plains. Sometimes they move as far southeast as the Midwest, but that'll pretty much be the extent of the troughing because these ridges get so strong off the southeast coast that that trough and the storm track stays well to the northwest. February 2019, look at this on the left. Well, the yellow coloring extending from Baja California across northern and central Mexico through the Gulf Coast and up to the mid-Atlantic coast. So we have ridging in place. We have the anomalies here on the right. And look at the disparity in the anomalies. And we're talking 8 to 10 degrees Fahrenheit above normal across portions of the deep south. And then we have temperatures in the Dakotas and in Montana that were 20 to 27 degrees Fahrenheit below normal. You can clearly see what the pattern looked like. The rest of the western U.S. also was below normal in the green coloring here. Arizona, Nevada, California, Utah, and parts of Oregon. So you clearly see the extent of the ridge, southeast ridge here, and it's really dominating things all the way up towards Virginia, West Virginia, Kentucky. Now this one didn't, the temperature anomalies didn't extend as far to the north into New England this particular month in February 2019. If you look at this very tiny insert up in the upper left of this slide, these were the temperature anomalies for the winter of 2018-19. Clearly see the maroon and the red coloring, very much above normal across the southeastern U.S., pushing its way northeastward towards the mid-Atlantic. Even the Ohio Valley was well above normal in the winter of 2018-19. Coldest air in that trough remained well back to the northwest over parts of the Dakotas, Minnesota, as well as Montana. January 2020, this was a very mild month. I think it was 76 degrees in southeastern Virginia around New Year's Day, if I recall. Actually, it was New Year's Eve. So it was December 31st of 2019. It was literally 76 degrees. I had traveled from the Midwest to come back, and I couldn't believe how mild it was when we got back here. 76 degrees. This yellow, this graphic here on the left, the 500 millibar heights and anomalies, the yellow coloring, the anomaly above normal heights from the western North Atlantic across the mid-Atlantic, up through New England and into southeastern and central Canada. And look at the anomalies for January of 2020. I mean, it was not even close to feeling like winter. Across the Carolinas, 5 to 6 degrees below or above normal, 5 to 6 above. Indiana, Ohio, lower Michigan, Wisconsin, Illinois, 5 to 7 degrees above normal. New England was 6 to 8 degrees Fahrenheit above normal in January of 2020. I took a look here. This is from Wavy TV, the local news channel. Anytime in this small little upper left insert here for Norfolk, Virginia, these are the temp anomalies in January of 2020. The pinkish colors there indicate above normal days. The blue coloring indicates below normal days. So there was 21 above normal high temperatures days in January of 2020 for Norfolk, Virginia. There's only 6 below average days. The January mean temperature for Norfolk, Virginia finished 8.4 degrees Fahrenheit above average. Just insane. What about February 23? This is a nice typical look of a 500 millibar height configuration for anomalies. You look at the deep oranges extending from Florida northward up towards southern New England across Massachusetts and Connecticut. This is a great looking example of what a Southeast Ridge looks like in winter. And this was a February of 23. The trough basically sat well off the northwestern U.S. coast, and this deepening trough just pumped up the heights across the southeast and mid-Atlantic specifically. And you see on the right here, this is your temperature anomalies for February 23. I mean, look at this. I mean, this is just insane how much above normal conditions were. And this is not slightly above normal, this is well above normal. 7 to 9 degrees Fahrenheit above normal from southern New York State, Ohio, western PA, down to Virginia, West Virginia, all the way down into the Carolinas, Georgia, to the Gulf Coast, Panhandle of Florida. Northern Florida, you're in there as well. The coldest temps remained over the western U.S. associated with this trough, with the purple coloring here on the left. And just to take a look here at the small inset here in the upper left, this is the 22-23 winter temp anomalies for the entire U.S., the entire winter, December 22 to February 23. Just look at the maroon coloring here across the east of the Mississippi River. I mean, it's just insane how above normal things were in that winter. And then the upper right, small little insert here. This is Norfolk, Virginia again, courtesy of Wavy TV. This was for February 23 temp anomalies. The darker browns, or the brown colors, indicate above normal temperature days, and the blues below normal temperature days. This was a month of February 23 at which Norfolk, Virginia finished 6.5 degrees Fahrenheit above normal for February. All right, so now that we discussed those temperature anomalies, I kind of showed you some examples of the height anomalies, the configurations of the 500 millibar heights, what generally indicates the Southeast Ridge. Let's take a look now. I thought this was interesting, and I'm just kind of throwing it out there. I just did a little research here on the back end of this presentation, kind of connecting the Southeast Ridge to the North Atlantic hurricane season. So my main thought is there a connection between the North Atlantic hurricane season and following winter pressure or height anomalies across the western North Atlantic? Here's what I'm thinking. If there's more tropical cyclone activity, that means we have increased low pressure during the hurricane season across the western Atlantic, okay? Increasing the low pressure frequency, right? So areas of low pressure, what would that mean? Would that mean there'd be an opposite effect or higher heights of pressure during the following winter season over the same area? My thought is equilibrium here. Equilibrium would be established through a pressure flip between the hurricane season, the late summer season, and the following winter season. So let's take a look now. I came up with these, off these blank maps. These are pressure and height anomalies and what I'm thinking, okay? So just bear with me for a moment. So the graphic here on the left, you see this red circle with these lines kind of spoking out from the center of this red shaded circle. This is a hurricane symbol for the North Atlantic, okay? So this is the months of August and September on the left. We have increased number of tropical cyclones, okay, across the western North Atlantic. So increased areas of low pressure, higher frequency of low pressure during August and September in the western North Atlantic. Based on what I'm thinking, we would have a pressure flip to higher the normal heights and pressure across the same area, the western North Atlantic, in January and February, that following January and February, the following winter. This would represent, this dark solid line represents the upside shaped U pattern I talked about, and this would be your upper level ridge. It'd be stronger than normal the following winters after increased low pressure and increased tropical cyclone activity in the western North Atlantic. Is there a relationship between the hurricane season in August and September and the following winter, January, February, and this pressure flip-flop? Let's keep going. All right, so now I'm flipping it. August and September, I have upper level high, height center. The Bermuda high is really strong. This black solid line represents the extent of the ridge. Look how far north that black solid line gets, the extent of the ridge, all the way up into southeastern Canada, well established in New England. So the ridge is dominant in August and September here on the left. All right, and that's during, August, September, peak hurricane season. And on the right, would that mean then the following January and February, we'd have increased frequency of low pressure extratropical storms and this trough off the east coast of the United States, off the southeast coast? But we have an increase in the number of nor'easters because of this pressure equilibrium. Here's what I found out. I'm using the same years. We're looking at North Atlantic hurricane season activity in these years. I use the same years that we looked at the temperature anomalies where we had a southeast ridge in place at some point in the winter. So all these years I've already used in this presentation, okay? This is a breakdown courtesy of Colorado State University. I looked at, what I'm basically using the number of tropical cyclones for a hurricane season, all right? And then just kind of categorizing the number of tropical cyclones to whether it's below average, above average, or average. Right, so you can see in 1982, we had 5 tropical cyclones. We had 1 subtropical cyclone. So that's not much low pressure going on in the western North Atlantic that hurricane season. ACE, by the way, is accumulated cyclone energy. It's a measure of storm intensity and duration across the tropical waters during the hurricane season, okay? But I'm strictly just kind of showing you the ACE values just for information purposes. I'm really focused in on the research on the number of tropical cyclones we saw in these respective hurricane season years. All right, so you kind of see how the hurricane seasons changed. I won't go down the line of every single year. You can clearly pause this video if you like and look at the different distribution of the number of tropical cyclones and the various ACE values, okay? And then I categorized these seasons again based on the number of tropical cyclones, all right? So you kind of see how seasons went from below average in 82 to above average in 1990, below average in 06, and then you went above average. We had an above average period from 2016, 2017, 18, and 19 were all above average years, right? And in 2022, we were at average. This is what I gleaned from that data, okay? The North Atlantic hurricane season activity and the following winter pressure height anomalies. When you see the red shading, the year, and then the results, you'll notice red is indicative of no correlation between the North Atlantic hurricane season and the following winter height and pressure anomalies, okay? So 1982, 89, 2006, 2015, and 2022 had no direct correlation between Atlantic hurricane season, North Atlantic hurricane season activity, number of tropical cyclones, and the following winter height and pressure anomalies. I would expect a flip-flop. If I have an active hurricane season, I should have higher pressure and more prevalence of the higher pressure or heights across the western North Atlantic the following winter. If I have a lower than normal hurricane season, lower number of storms, that means I had higher pressure or heights more so than low pressure in the hurricane season, and therefore I should have the opposite effect. So I have higher pressure. That means if it's higher pressure, lower than normal season in the western North Atlantic, I should have lower pressure the following winter. Look at the green coloring. This is indicative of the correlation. 1990, okay? We saw above average hurricane season in 1990. So that means we had more low pressure across the western North Atlantic than normal. In the following winter, specifically in December, when we looked at December 1990 previously in this presentation, we saw the upper ridging over the East Coast and the presence of a Southeast Ridge. 2016, we also saw a correlation. 17, 18, and 19, we saw correlation. So it's interesting that 2016 to 19, we saw above average hurricane seasons, the number of storms, and we saw at some point those following winters a strong upper level ridge develop. Okay, that is really intriguing to me. 2016 and 19, above normal hurricane season, and then the presence of a southeastern ridge or some sort of upper level ridge, anywhere from the Gulf Coast to the Mid-Atlantic up the eastern seaboard. So that's really interesting to me. So overall, I wanted to show you the data. I wanted to show you whether, hey, it matched up to what I was thinking, whether there was a correlation in green or no correlation in red. Here's my findings now to conclude this presentation. I looked at 10 years. I studied 10 years of data. 5 of those 10 years, 50% of the data showed a potential correlation. And I'm just basically taking that right from here. Okay, I'm putting the findings directly into words from this data. So 5 of the 10 years that I looked at, 50% showed a potential correlation. In 5 of those 10 years, the red coloring, right, show no correlation between North Atlantic hurricane season and the following winter height and height anomalies, higher height anomalies over eastern U.S. associated with a ridge. And although it would make sense to see higher than normal pressure or heights across that western North Atlantic Ocean in the winter, the following winter, after an active hurricane season, with lower than normal pressure heights during the hurricane season, the atmosphere is rather complicated. It's not that simple. There's positive feedback mechanisms, for example, between the ocean itself and the overlying air. It's also very difficult to determine both the temporal, the time, as well as the spatial distribution. What areas are covered? How big does the box get? We're talking energy here. We're talking a major area ocean. Teleconnections or global climate drivers may be more responsible for any hurricane and winter season pressure or height anomaly correlations. I didn't really look at the teleconnections. For example, if we had a La Nina, we typically see an upper level ridge, establishment of that Southeast Ridge. It's more favored during La Nina winters off the U.S. Southeast coast. And that would result in milder temps for the Southeast and Mid-Atlantic. Additionally, the stratospheric polar vortex, that may be disrupted, and that will result in major changes in the polar jet stream, where the placement and the amplitude of those troughs or ridges set up. But no matter the cause, there has been an increased tendency for the Southeast and Mid-Atlantic to be influenced or impacted by the Southeast Ridge at some point with above average temps during the winter season. And finally, this is my last slide. Since that record warm month of December 2015, we have seen 6 winter months influenced by the Southeast Ridge with well above normal temps across the eastern U.S. And in some cases, the ridge has been so strong to produce record temperatures, whether they're record high temperatures or record minimum or low temperatures. Record warm sea surface temperatures also could be partially responsible for building stronger upper level ridges during the winter season across that portion of the Atlantic Ocean, the western North Atlantic. We're seeing a lot of record warmth in the global ocean right now as far as water temperatures go. And then finally, I do believe that more research as to what specifically causes the Southeast Ridge to be a strong synoptic influence during the winter season, it needs to be conducted more research. Like I said, there's a lot of variables here. The spatial temporal domain is large, covers a longer time period in some cases, teleconnections, stratospheric polar vortex behavior. All this could possibly correlate and tie in with my findings here. But I thought it was an interesting topic. That concludes this presentation. I really like this idea. It makes a lot of sense. When you have an extended period of low pressure in the western North Atlantic during hurricane season, that should be compensated with higher pressure, higher than normal heights at some point. Maybe it's the following winter, maybe it's the preceding winter. I didn't even look at the preceding winter prior to the hurricane seasons. I started with the hurricane seasons and looked at the following winter. So just some ideas and some thoughts. And I really hope you enjoyed this presentation. I got a lot more to come. Let me know if you liked the video. Thank you for subscribing to my channel. As always, I appreciate each and every one of you. And that's all I got for now. Until next time, everybody, take care and God bless.